Hi, so today I want to present some work that we recently finished with this group of people from the University of Tübingen. And the basic idea of this work is that we want to do nonlinear disentanglement, and I'm going to unpack in a second what that means, on natural data with temporal sparse coding. And the very simple idea behind this is you can't do disentanglement if you only have images. But if you have natural videos, those have specific statistics, namely objects only change a little bit in time. And if you have the right prior in your model, you can actually do nonlinear disentanglement. So that's the very simple idea of this pitch. So let's dive in. What is disentanglement? So assume you have a description of the world. Let's say you're in a very simple world and everything is fully described by its shape, scale, orientation, and position and XY coordinates. Now we can synthesize images, visual images from these world states. This is sort of like rendering them with a graphics program, and then you get some observations. So in this case, these observations come from a well-known dataset, Sprites, that's often used in disentanglement research. And you basically see that there's shapes at different positions with different orientations and different sizes. And now the question, what is disentanglement, is basically the inverse direction. You wanna start with these observations, analyze them, and then retrieve back the state of the world from these observations. Now it's a well-known result in a similar discipline, which is called nonlinear ICA, nonlinear independent component analysis, which is all about line source separation. And it's been a well-known result from the 90s that if your sources are independent and you don't know them, so it's blind, and your synthesis is nonlinear, so these sources are somehow mixed in a nonlinear way, then you're lost. And it's basically not identifiable. There's no chance that the model you learn will be picking out the right states of the world. I'm not going to go into details here. You can read that up in the reference down there. But that's an old result. All right. So the question that we started asking at the beginning of this project was, what about time? Well, what about time? So the world does not only have a state at any instant in time, but it's also changing over time. So we basically said, okay, let's take the state of the world and let's add dynamics. We went to YouTube, and YouTube VOS is a well-known segmentation dataset of YouTube that's basically segmenting objects in YouTube over time. And we measured how much do they change in position, that's delta x and delta y, and how much do they change in size. So these are like some of the factors that you see above in the state of the world. And what we found in that natural data is that those factors changed extremely sparsely. Most of the time, they do not change at all, and sometimes they make rather large changes. So in blue, these are histograms of those changes, and in orange, we fitted a distribution called a generalized Laplacian distribution with a specific shape parameter. And if alpha is 1, that's a Laplace, it's much smaller than 1. It's usually around 0.5. And that means that these distributions are extremely sparse. So that's where the temporal sparse coding in the title comes from. We basically see that natural objects change extremely sparsely over time. Now with this idea, let's revisit the setup that we had just now. We're gonna push these through a synthesizer, and this time we end up with observations where we always get image pairs. So this is like the minimal sequence length that you can imagine. We always have xt minus 1 and then xt, the next pair. And what you see here is that those pairs are rather similar. Like you would expect in a movie, things don't change too much over time. They change a little bit in position, they might come closer to you, so they get larger, and they might rotate a little bit. But there's not too many changes. Now, if we take these observations and we train a model and we want to find out, can we have some analysis model, and usually this is a deep neural network, can we identify, or can we get back to the original state of the world? Can we identify the sources? And what we show in our work is, yes, we can identify them if the world is changing sparsely and if we use this with the right sort of probabilistic prior in our model. Now, this is not a new thing. So I think the first reference, to the best of our knowledge, was Feljak in 1991, who first explored this idea. Can we maybe learn more about our data if we consider the temporal structure as well? That things in time change in specific ways. And then recently, Vivarin and Morioka showed that if you assume such temporal transitions, nonlinear ICA also becomes identifiable. However, their work is a little different to ours because they don't allow such sparse transitions that we have. In fact, assuming a generalized Laplacian like we did in those histograms there, alpha equals 1, so Laplace is already no longer covered by their theorem. And they also don't have, it's a contrastive learning objective. So you only learn the analysis platform. Whereas we also learn a synthesis model and we do variational inference. But I'm gonna go into detail in the next slide. So this is cool. Now we can identify those sources. Here's a little intuition about how we prove that now we can do this. And this is very high level. If you want to hear more about the details, just look at the paper and go through the proof and read it up there. So we start again by looking at those transitions. And basically what they give us is an inductive bias that says, okay, objects in nature change sparsely. So how could we translate this into a prior distribution for our parameters in a model? Well, assume you have a two-dimensional parameter space with x and y position, and you somehow want to condition the position at the next time step on the position in the previous time step. So that's zt minus 1, that's the previous time step, and then zt, that's the next time step. And what we say here is, okay, we're going to take a sparse distribution. So here again, it's a generalized Laplace distribution. The blue x is zt minus 1. And then we just say, okay, we take a generalized Laplace distribution, we center it at the previous time step. And that gives us the probabilities that we might expect to observe at the next time step. And what you basically see here in this distribution is that it's likely to be somewhere on the axis in the next time step, and unlikely to be somewhere on the diagonal because there's much less mass of the probability distribution. Now, by using this fact, let's see how we can identify the parameters in a model. So here on the left, I'm showing you the parameter space of our true model. So this is the one that we want to learn. And there's always pairs of blue dots. And each pair represents one transition that you observed in your natural data set. And what you see is that they're mostly aligned with the axes. And that corresponds to this intuition that transitions tend to be sparse. Now assume on the right side, we've learned a model and we've got it wrong. So the model, this is now Z0 and Z1 without the stars. They've also learned a representation that's aligned with respect to their respective coordinate system. So you see that the red lines are aligned to Z0 and Z1, but they're rotated with respect to Z0 star and Z1 star. So we've learned a representation in this model that's that fulfills the prior for the model, so it's aligned, but it's rotated with respect to the original model. And let's see now what kind of problems this causes. So if we generate stimuli, or if we generate image pairs from the model on the left, that's a ground truth model, we see that, so like for instance here, we have a white square in the first time step, and in the next time step, it has made a large jump in X, but no jump or no change, or only a small change in Y. And we're going to observe a lot of these pairs where like one factor changes but not the other. If we now generate images from the model on the right, we will see that most of the time these will actually change in both factors, because as you can see in the diagram, the usual transitions, they are sparse in the model space in Z0 and Z1, but they are dense in Z0 star and Z1 star. So most of the time you will see that most of the factors are changing when you generate image pairs. And what this means is that the distributions that we get from these two models, it'll be sparse transitions for the ground truth one, and dense transitions from the model that got it wrong. And this is basically the starting point and also the ending point of the proof, because at the beginning of the proof, what we assume is that we learn a model which matches the distribution of image pairs that we observe. And then basically you see here, if you have a model that gets it wrong, then it can't have matched the right distribution of image pairs. So by forcing our model to match the distribution, we will have to learn a model that is aligned with the ground truth model up to some permutations and sign flips. And that's the intuition of the proof. Again, if you want to hear more, please look at the paper. Now, how do we implement this? And we're building on a well-known framework, variational autoencoders. We're starting with our observations again. We send them through an encoder, so that's the analysis part. And then for the first time step, we're doing the same thing like people always do in autoencoders. We have a standard normal prior for the first time step, and then Q is the variational posterior. If you don't know what that means, please look at the original paper. That basically gives us some encoded factorized Gaussian distribution for the first image that we see in a pair. Then we decode it and we measure reconstruction error, and you can train a model like that. Now the thing that we add on top of this is, now that we have image pairs, we also need a prior for the second time step. And this is where we implement that simple idea that things change sparsely in time. We're going to say, okay, the blue cross is always at the same position in these three plots. And it's basically the mean of the variational posterior of the first time step. Around that mean, we're now going to plug in our sparse transition prior. So that's P of ZT given ZT minus 1. And basically that says, okay, for the next time step, I want you to be close to that position. And if you're away from it, then ideally put the next embedded posterior mean on the axis. And that's what you see there on the right. And that's basically all there is. You can look at our paper to see the derivations for how this works out in the formulas. But again, here's the simple intuition of what we're doing. Now let's look at some results. And here's a standard way of evaluating these models in disentanglement research. We're basically going into the learned latent space. So a few slides ago, this latent space was just two-dimensional x and y position. Now we have a 10-dimensional latent space because we also need to encode some other things. We're going to this latent space now, and we just walk through the latent space and push everything through the decoder and see what kind of image sequences we're generating. And ideally, what we want to see, if this model really has identified the correct sources or factors of variation, then we should see that as you turn up one of those knobs, only one factor should be changing. And here's a trained model with our approach, and we see that indeed latents 5 and 6, so Z is that latent space, latents 5 and 6, they've learned to encode the position, latent 4 is encoding the size, latent 2 is presumably encoding something like shape and a bit of orientation, and it's getting hazy there. One problem with this is that this is not optimally suited because this model setup, because rotation has cyclic boundaries, and then shapes don't really have a topological structure. So these two factors are a little tricky, and we don't expect perfect performance here. This would be like, it's just not perfectly matched to the assumptions that people are making here. All right, so this is a qualitative check that it's looking good. A quantitative version is that we take a lot of images for which we know the ground truth factors. We push them through our encoder, and then we compare them. We basically check how well can we decode the ground truth factors, and how much are they restricted to single latent units. And there's a lot of metrics out there in the literature that people are using. Here's a little selection of 6 of those. So this is an open research field. I think it's not yet decided what the best metric is. But across those metrics, beta VAEs is a standard model that's basically not using any temporal information. The model in the second and third row are from Locatello et al. 2020, who are using a similar setup where they have some temporal supervision, but as we argue, in a much more artificial way. And then below you have our model, the SlowVAE, trained on their data and trained on our data. And basically what you see is that across those metrics, we're robustly outperforming the previously proposed models. So that's a cool thing. There's also other data sets and more experiments and visualizations of the latent spaces in our paper. If you're interested, please check it out. One other thing that I wanted to show you here is another data set that we introduce. Unfortunately, some of those latents are not showing. Basically, what you should be seeing here on the left is segmentation masks of pedestrians walking around. And this comes from a self-driving car dataset, KITTI. And we basically took those segmentations and only looked at the segmentation masks across time, because textures and a lot of real-world factors, they're basically at this moment too much for this easy VAE setup. So here's like a little digested version of natural movies that we can handle in a VAE setup. Now they're disappearing more and more, but you get the idea. It's basically pedestrians, videos of pedestrians across time. And you can imagine that you could get those segmented objects with some sort of instance segmentation algorithm. So it's not too far-fetched or like too much to ask that this is some pre-processing step in your machine learning pipeline. All right, so this is a natural data set that we wanted to look at. So first again, let's look at the decoder. And let's turn those knobs up and down. And what we basically see is that the latents are becoming organized. So for instance, every column now represents one latent unit with different starting images in each row. So in the third column, the third latent, you basically see that it's encoding something like the size of the pedestrian. The latent units over here, so that's 6 and 7, they're encoding something like X position. And you see here that there's a little person stepping over. These weird diagonal movements are a lot in the data set. That's basically when a car is driving at a slanted angle along a pedestrian. And then in the last latent units, you see that there's a Y translation. So the person's coming down on the screen. So here's, well, a bunch of transitions that you're likely to see in nature and that can be thought of, or like that that can be independent of each other. Of course, these are not exactly independent, but that's another future question to ask. Okay, so the second thing we wanted to look at was numbers again and comparing it to other models. The problem here is now that we don't have ground truth information. So we took the measured X and Y position, so that's the center of mass of these segmentation masks, and the size of them. And these are basically our 3 simple ground truth factors. And then we compute another metric that evaluates how well you've identified the different sources. And we compare it to, again, the standard model, beta VAE, and then our model. And you basically see that as you increase the separation between the frames, so t equals 1 means we're taking adjacent frames, t equals 5 is 5 frames in between. You see that you get much better at disentangling these different sources. So again, the idea seems to be working out. And we're also releasing this dataset to encourage the community to move more towards natural dynamic datasets. Okay, let's wrap this up. What does this mean now that I've been talking about? Well, objects in nature, they change sparsely. We've shown that with a sparse transition prior that picks this up, those sources can become identifiable. We've shown empirically and theoretically that this works, that you can identify the sources. It's not always perfect, but it seems to be working. And on naturalistic datasets, we learn meaningful representations. Okay, so what are possible future directions? Here are some questions that that came up during the project and that we'll be looking at in future iterations. One is, how could this scale to real complex scenes with multiple objects, occlusion, with complex textures, and possibly with dependent factors? And then another question is, might biological systems be using some similar strategies to learn how different sources or like how different properties of objects could change over time? I think there's this is not going to be a simple answer. It's going to be mixed up with many concepts about how people learn, about how objects move, how they are permanent across time, etc. But I think this links up, and here are like some initial hints, and we're going to look further into how this relates to a lot of literature in developmental psychology. Okay, these are the people who've worked with me on this project. Lukas Schott, Yash Sharma, and I have mostly been running the experiments. Dylan has been the senior lead on this project. And then Ivan, Wieland, and Matthias have given some input on this as well. And these are the references. And I hope now that you're also excited about identifying the sources, the real sources, and factors of variation on natural videos, and that you'll be checking out the paper and exploring further directions in your research. So long.